Today I'm going to talk about satellite laser ranging. The principle of laser is very similar to the two-way system of distance measurement. For example, what was a two-way system? Let me explain the two-way system first. Two-way system is that I have a sender, a transmitter here, and I have a reflector somewhere. This is a reflector, and this, for example, transmitter. The signal is sent to the reflector and receive the reflection. The travel time of the signal, which is actually delta t, for example, is when the instrument send the signal, it records the time, and when it receives the signal, it records the time, and when this is subtracted, this is the total time that the signal has been on the way. We divide it by 2 and multiply it by the speed of the light, we get the distance. We divide it by 2 because it's a two-way. One goes to the reflector and one goes back. This means that the time is double. Travel time is double. So one is twice larger than the distance. The time that the signal received. The signal comes to the reflector. That's the principle of ultimate distance measurement using two-way system. The satellite laser ranging actually has the same principle. We have a telescope number, and we have a reflector, which is on the satellite actually. Reflector, and the signal is sent to the reflector, which is the satellite, and will receive. So we have a transmitter actually here, and we have a receiver. But it's not only that, because we have to create the laser. We have an instrument to generate the laser, and when it's generated, it is sent to this transmitter, and the transmitter sends it to the. When it is received, it comes back, and it will. We will do a signal detection. I will explain what is it. And also we have a control orbit prediction. Of course, computer and atomic clock to measure the time precisely, because the speed of the light is too high. And this for measuring the time is very important for both when the signal is sent and when it's get back. So it's very important. So this is the system works like this. This is the figure 8.1 in the figure 8.1 of the book, Satellite Geodesy. What I'm going to explain it. One SLR system has a transmitter, a receiver, and a detector. What is this one? Is laser is if you create a laser, it is done in a place inside somewhere, and there is a special instrument, and this light is somehow transferred to this telescope to send it for being sent to the reflector, to the satellite. And the detector, when the signal is going to the reflector, it has a power, but when it's reflected back, the power is reduced significantly. Therefore, among all received signals, we need to detect and find which one of these signals actually are the reflection of the laser that we have sent to this reflector. Therefore, we need a detector here for doing that. And of course, the time, measuring the time is important, because this travel time of the laser is going to be measured and divided by 2, multiplied by to get the distance between the lasers, the telescope, and the reflector. So generally, what is measured is the distance between the telescope and the reflector. So one thing you have here is what computation of the orbit. What does it mean? It means that in past, when they have not possibility to measure to measure the orbit, they had to find the satellite in the sky and with a telescope, and then send the and they shoot the laser to the satellite. But nowadays, everything is fully automated. So it means that the orbit of the satellite is predicted based on this Kepler's laws, the perturbation forces, and we can predict the approximate position or predict the satellite positions, and a system will automatically, based on that predicted position, will find the direction to the satellite. So to these days now we use this orbit, or the ephemeris of the satellite, which is already available. So that's the principle actually of a satellite laser. It's the satellite laser ranging principle. Laser ranging has had 3 generations. What does it mean? In the beginning, it was the first generation. The first generation, the quality of the measurement was not that good, and the pulse length was about 10 to 14 nanoseconds. Consider that 1 nanosecond is equivalent to approximately to 15 centimeters. So pulse is the pulse is like that. The wave is moving so like this, but pulse is like that. You send the pulse, and this pulse is moving towards the target and comes back. This pulse size is that one actually, pulse time. So if this, for example, 40, if you multiply 40 to 50 centimeter, you can see how accurate will be the distance between the satellite and the receiver. So the second generation will be the second generation. The pulse is between 2 to 5 nanoseconds. It's big because of the advance in technology and measuring the time better. And the third generation actually is between 0.1 to nanoseconds. It means that it comes to accuracy of about 1 up to 3 centimeters. So nowadays we can measure the accuracy, the distance between the telescope and the satellite with accuracy of 1 up to 3 centimeters, which is really good. Maybe these days even 2 millimeters. However, there are problems actually for using satellite laser ranging data because of the separation of the satellite stations. For example, if we have over continent and we have some stations over continent, that this distance between these stations are too long, and these are actually not like a GPS receiver that you can carry simply from one point to another. They are actually big institutes or buildings there to do these things. So this is very hard to actually, this is not possible for the mobility, but we will see that there are some containers like a big truck, they have, and they move around, and they have this telescope and everything on that. They move around, but even so, if we cannot use satellite lasers everywhere. We have very limited coverage actually over it. So, for example, over a continent, if we have over continent at some point over another continent, and we do laser ranging, we can measure how much these points can move with this relative to each other. That's possible. But for example, if you want to do orbit determination, you need at least 4 stations from different places to reach. So it is not always possible. And because the satellite path maybe for a short while you can have, but not for long. So this orbit determination actually based on satellite laser ranging, only the satellite laser is not actually very successful. It's not possible. I cannot say that this is impossible, but it's not working well, actually, I would say. So, but if you have other type of these systems, for example, if you have GPS on the satellite, so then that's good. Then these SLR systems can give you extra information and a lot of maybe something like constraints for improving the quality of the orbit. For example, we know that these days satellites like Grace Goose, and they have some reflectors under them, some reflectors for SLR reflectors. So with one station, for example, if the satellite passes over one station, so you cannot determine the coordinates of the satellite using only one station. But if you write a system of equations for measuring this, for determining the coordinates, you can add this range as an extra, as a constraint. Constraints for example, this range, of course, you have to linearize. It can be something. This is a constraint in the system, and when you solve it, this will have, because of this high accuracy, it will have huge contribution to the station coordinates. So therefore, or if you give it as a constraint, even better. So for is a better or weighted constraint. So this is what I want to say, that SLR system is good. Let me write it here for you. SLR